minus 1 polynomial. Minus 1 plus over. So let me write it here. And this is also not precisely the space, because the map phi should have degree exactly d, not less than d. So I need from these two polynomials the condition that they do not have common roots. I need them to be the resultant. I need resultant of these two polynomials. One. So to be what? To be non-zero. So this is the space of maps. Now you see, as it is written here, this space is an open subset in the affine space. So the natural idea is to, sorry?
The degree in this case is, what is the degree in this case?
The degree is just degree of this map from P1 to P1. And it is the degree of the polynomial.
And in the general case, the degree, what is the degree?
And in the general case, well, I have a map from P1 to the flag variety. So how to define the degree? There are several ways to do it. Maybe the most natural is the following: you have the tautological flag of bundles on the flag variety. So flag F1, so on, F n-1. Topological. Right. Then you can pull it back to the P1. So consider pull back. So on. One. Then the degree of this map is the collection of the degrees of these vector bundles on the P1.
Perfect.
maybe negative of the degrees. So these guys should have degree minus E1 on then minus En minus 1. So, and actually, this description suggests some way of compactifying this space. Not precisely compactifying, but some way of taking a closure of this space. Namely, you. So here, this map phi is uniquely determined by this flag of sub-bundles in the trivial bundle, right? So to take a closure, you just allow these vector bundles to be not sub-bundles, but sub-sheaves, to be a flag of sub-sheaves in one, in each of them, and in the next. Okay? So now in Fi plus 1, not necessarily some bundle. So then you get slightly bigger space, and let me demonstrate it on this example. So again, let me write it here. So let me denote this closure of MD as QD. Right. Is by definition the space of all possible flags of sheaves of locally free sheaves. One. Such that rank of Fi is I, and the degree of Fi is minus I. So MD is naturally contained in this space. And in this example, actually, UD you can obtain QD from MD by just removing the conditions. So you have to consider just space of pairs of polynomials of this sort. The same, but with this condition removed. So QD is called Lamont quasi-flat space. And it is known to be smooth quasi-projective closure of MD. One can take, it is quasi-projective, so it is some resolution of the spectrum of its coordinate ring. So it maps onto ZD, which is just spectrum of the global functions on QT. Okay, so and this is called Drinfeld zastava space. So this space is no longer smooth. It is outside this n equals 2 case. So it is a singular in general. But still it is interesting, and this resolution of singularities is known to be small. This is resolution. This is a result of such a present. So, in fact, for me, these spaces are interesting because they have some geometric representation, carry some geometric representation theory. So actually, you can obtain some representations of finite W algebras in localized equivariant cohomology of these spaces, but I won't talk about this today. Maybe sometime next time. Okay, so now I will speak about symplectic structure here on MD, which extends to a Poisson structure on both Drinfeld zastava space and on the resolution.
Could you just repeat what is the zastava Drinfeld space in this simple case, in the most simplest case?
In this simplest case, we have they in fact coincide. QG is ZT. Because in this case, QG is already affine.
Okay.
So nothing changed. But for SL3, they are already different. So actually, for n equals 2, yeah, so MD is an open subset in C for to D, and this is MD. Now, let me describe a Poisson structure. On D, which is in fact symplectic on MD. It's non-degenerate, but it will extend to these closures as a Poisson structure, not as a symplectic structure. It will have zeros at some point. Okay. Definition goes back to so college and for n equals 2 it is actually Atiyah-Hitchin bracket. So let me give a formal definition. So to define a Poisson bracket, I need a morphism from the cotangent to MT to the tangent of MT. Now, what is the tangent of MD at the point phi? It is just the global sections of the pullback of the tangent bundle from the flag variety. But since we are considering base maps, it's listed by O of minus 1. Okay, so the dual space, this is because we require that phi of the infinity something fixed. So the cotangent space is the dual of this, so it is H1 of E1 the pullback of the cotangent variety under O of minus 1 again. By the Serre duality. So I want a map from here to here. I will obtain it from the following complex of bundles on the flag variety. So consider the following complex. C star of the flag variety. In fact, the trivial bundle with the fiber being GLN. So this is an embedding. There is a surjection onto the tangent. So why it is a complex? Because what is the tangent space to the flag variety at some point, at some flag? This is the quotient of GLN modulo the Borel subalgebra preserving this point. And the cotangent is the dual of this space, which is the annihilator of the Borel subalgebra in GLN with respect to the invariant pairing. But the annihilator of the Borel subalgebra is the maximum nilpotent subalgebra. It's commutant. So it is naturally contained in V. So when we embed this into GLN and then project to GLN mod B, we get 0. So this is the complex ensemble. So next we can pull it back to P1 and write the corresponding spectral sequence which compute the hypercohomology. By this map phi, and take the second differential in the corresponding spectral sequence. So D2 in the spectral sequence computing hypercohomology, what we get will be a map from this to this, from H1, pull it back and then make it 10 minus 1. And when we take D2, it will be a map from here to here. Phi star. So this is the most natural definition of this Poisson bracket. Actually, what they did in this four authors paper, they wrote this D2 in some coordinates and saw that this is in fact a Poisson bracket. So it satisfies and check this in coordinates. Now let me write these coordinates in the case of SL2 in the n equals 2 case. And the following coordinates. So x1 on xz is the roots of the polynomial p, and another complement set of coordinates is y1 yd, being the values of q in these roots. Q. So actually, these are coordinates on, well, étale coordinates, so they are coordinates on some fine covering of this MD. But it is sufficient to compute the Poisson bracket in these coordinates. So, and in this case, one has xi at j 0 and yj is 0 also. Well, xi j is ij yj. So xi and log of yi are canonical coordinates.
Log canonical.
Yeah, so they are log canonical. Okay, so in the general situation, you have some similar coordinates, but to write them, you need something more about flat variety. So you have to realize flat variety as a closed subvariety in the product of projective spaces. Namely, you take the Fluker embedding. Yeah. Projectivization of the exterior powers of Cn. So given a map from P1 to the flat variety, you get a collection of maps from P1 to the projective spaces. And what is this? which takes z at some point here, which it has some homogeneous coordinates. I of z for all subsets I in 1n of cardinality I. So now the role of the polynomial p is played by the very first of these a's, pi in ui the next one. So it will be a 1, so on, I minus 1, I plus 1. You can do the same. You can take, so this is going to be a monic polynomial, z to the power di plus something, and this is going to be a degree d minus 1 polynomial. So you can take the set of coordinates x, I, r, the roots of I and y, I, r, with the values of ui in this root. Then the bracket of SIR as JS is always 0, and the bracket of XIR YS is delta I J delta R S Y J S. So they are almost log canonical, but the Y's are maybe not so good. So the bracket of YIR YJS is 0 if I is not j plus minus 1. And it is y r y j s over x I r minus x j s otherwise. And after it is written, it is an easy calculation to check that it satisfies the Jacobian game. Now, so my goal will be to quantize this Poisson structure. Namely, to write some deformation of the algebra of functions on the zastava space, whose classical limit is restricted.
Leonie, excuse me, is it a good place to some question about the classical part? How it is related with the Poisson structure in cluster algebras, which are some definitive condition for cluster seeds? Do you know some relations? Because the formulas are very...
Well, this bracket is not cluster, because for cluster varieties, we need actually something like the bracket of x and y to be proportional to x, y, to be some linear combination of the, to be quadratic. Actually, we need it to be quadratic, not linear. So, well, in fact, we expect that the trigonometric analog of this space has a cluster structure. But actually,
okay. Another
in
question.
fact, yeah, at some point we wrote some coordinates which look like cluster, but we didn't prove anything.
Okay. Yeah. Another question.
But all this about the trigonometric analog of this, not about precisely this.
Okay. Another question about some more general interpretation of the Poisson structure. Do you know something more general invariant definition of this Poisson structure?
Well, in fact, this this generalizes to actually to spaces of based maps from P1 to partial flag varieties, and even for to partial flag varieties for affine for loop groups. And maybe I will say something about this at the end of the talk. And on the other hand, this is as Nakajima noticed, this is also a particular case of what he calls bow varieties. So and this follows actually from quiver realization of Drinfeld zastava space. So in fact, I use quiver realization for quantizing this. So what I'm going to say next is just because I'm going to describe the quiver realization of this.
Sorry, Lebedev, may I also ask a question?
Yeah.
This is about the case n equal to 2. The Poisson structure you have written out is very similar to that of Atiyah-Hitchin Poisson.
Yeah, it is precisely Atiyah-Hitchin, yeah.
But Atiyah-Hitchin seems to be different because the bracket of the roots is 1 over the difference.
1 over
It's not 0.
1 over the...
Like in the last formula on the blackboard or something like that.
Okay.
Okay,
yeah. Okay, so maybe yeah, maybe well, sorry, I'm not sure.
yeah, and one more question. In addition to Atiyah-Hitchin Poisson structure, there is a family of Gechtman and I don't remember who.
Gechtman Shapira, right?
Not Shapira, I believe. There is somebody. This Poisson structure is not unique in a sense. It is of a family. Is there such a family in your considerations?
You mean there is some pencil of brackets, some compatible brackets?
Yeah, exactly.
Yeah, in fact, we do not consider other brackets on this space, so I don't know.
Okay. I can.
But it is interesting, right? Thank you. Okay, so now the quiver of QG and ZZ following. So it is similar to Nakajima quiver varieties, but it is in fact different. So let me write a quiver. So I'm considering the spaces D1, D2, so on, n-1. So it's the dimension of Pi and Di. And the map between them is B. The map from each of them to itself, which is denoted by A. And also some additional one-dimensional spaces, W1, W2, and so on. -1, along with maps U. Going this way. So I am considering the space of all representations of such quiver with the condition A B minus B A plus PQ equals 0, modulo the action of product of GL. So the theorem that this quotient, so the categorical quotient is ZD this categorical quotient is ZD, and the GIT quotient with respect to some stability condition is QT. And this is the resolution of. Now, let me briefly explain how to pass from Lamont quasi-Flux space to this quiver variety. And before this, actually, I noticed that unlike the Nakajima quiver variety, we do not have arrows going in reverse directions. So the usual way of defining symplectic structure on a quiver variety gives identically 0 here. So to define a Poisson structure on what we have here, we need something different, not the usual Nakajima procedure. Now let me briefly explain how to get from QD to this quiver variety. It is called actually a Hansel quiver variety because the form of this quiver is a Hansel. Okay, so okay. So what is the Lamont space? It is the space of flags of subshape in the trivial n-dimensional bundle F1, F2, and so on, Fn minus 1, and F1. Now, such that rank Fi and Fi. So So, and also I consider base maps, so this flag is trivialized. Okay, so I have H, well, the global sections of Fi tensor of -1 is 0. So from this condition, we have that H1 of the same bundle is exactly di dimensional, and it will be di. Define di as the first homology of Fi of -1. Next, from the exact sequence 0 to Fi of -2 to Fi -1. So the skyscrapers here. Fi infinity. I have a one exact sequence. Zero. Which is H0 of Fi of -1. So I-dimensional space, which I write W1 plus so on plus Wi. So the dimension W1 is of the skyscraper sheet. So this flag is trivialized and fixed at the infinity, that will fix to be the standard flag at infinity. So this is just the standard I-dimensional subspace in the n-dimensional space. It is something. Next, I have H1 I -2 and the di at the end, which is H1 F. So this is an exact sequence, and in fact it is split. So it gives me the identification of this first homology space with W1 plus so on plus WI plus I. Now next, I have a map from W1 plus so on plus WI plus DI to DI coming from multiplication by the coordinate Z. Multiplication from Z from I of minus 2 to Fi minus 1. So the components of this map give me a map from maps from Wi to Vi, which is P, and from Vi to Vi, which is A. So next, now from the map from H1 from I of minus 2 to Fi plus 1 from the embedding Fi plus 1 of minus 2, I have a map from W1 plus so on plus Wi plus I to W1 plus so on plus Wi plus 1 plus Fi plus 1. Taking the component which maps Vi to Vi plus 1, I get the map P, and actually I'm taking the component which maps Vi to Vi plus 1, I get Q. Now the relation I wrote here, that AP minus BA plus PQ 0, follows from the commutativity of the following diagram. So this actually follows from H1 of I minus 2 to 1 of I plus 1, 1 I 1, I plus 1, 2, this one. And this relation follows from So of course, once you constructed a quiver from a point of in the Lamont space, you have to check something. So you have to check that what you get is an isomorphism, and this actually can be done, but let me skip this. Now, let me define the Poisson structure on this Poisson space. Let me again draw the quivers and write the relation. So I have the quiver B1, B2, B1, and one-dimensional spaces W1. With the relation AB will be A plus BQ 0. So the best way of defining a Poisson structure on something is to realize this as some Hamiltonian reduction. So for this, I want to realize this as 0 of some moment map with respect to this group. And let me then define a Poisson space acted on by this group such that 0 of the moment map is this. So this Poisson vector space will be a coadjoint representation of some Lie algebra. Algebra such that, so what I want actually to define some Lie algebra G such that there is a Poisson subvariety in its coadjoint representation, some S, acted on by GL D for this product for GLPI, such that Hamiltonian reduction is this. Let me define this G. So let me cut this picture, this quiver, into triangles. So let me take for any triangles with the vertices vi plus 1 and wi plus 1. So to any such triangle, I assign a Lie algebra. Vi plus 1, wi plus 1. I attach a Lie algebra. Let me denote it Gi, which is the following thing. It is the semi-direct product of GL Vi plus GL Vi plus 1 acting on some important radical Ni, and Ni is just two-step nilpotent Lie algebra which is formed from Wi plus 1 to Vi. Wi plus 1 is one-dimensional, so let me better write it as Vi star. Vi plus Vi plus 1 star plus con Vi plus 1 Vi. The commutator is the following. This is the center. The commutator of these two guys is just the product, just the tensor product of this, which is here. So I define an important Lie algebra, which is actually a Heisenberg type Lie algebra. So this is the center, and the commutator is always in this center. It is just the tensor product of this and this. This nilpotent Lie algebra is acted on by GL Vi on the left and GL Vi plus 1 on the right. So one can take the semi-direct product, semi-direct sum actually of GL V plus GL Vi plus 1 and this nilpotent algebra.
Excuse me very much. I have some physical restriction. I have a train to Moscow.
Okay, I see.
10 minutes. Do you have a chance to explain the end of the story now, or we could postpone this discussion?
I can. Well, actually, right. So I can finish maybe in 5 minutes, or
it would be
okay.
Yes,
it will be good. Okay. So anyway, so our main result is actually that I can take the direct sum of all quadrant representations of such Lie algebras over all triangles in this quiver. This is a Poisson variety, and it has some natural Poisson subvariety. Actually, each of these quadrant representations has a Poisson subvariety determined by some equation like this. or some subvariety, such that the Hamiltonian reduction over diagonal GLM of VI. So GLM of VI is contained for each VI. The GL of VI is contained in two different Lie algebras, in two neighboring Lie algebras. So I can take the Hamiltonian reduction by the diagonal embedding of GL VI for all these VIs.
Okay.
So this is the realization of this query variety as some Hamiltonian reduction of the Poisson. And moreover, this realization is good for quantization because you know what is the quantization of the coadjoint representation of the Lie algebra. It is just universal enveloping algebra. So you're just taking the universal enveloping algebra, take a quotient of by some two-sided ideal, quantizing this. Actually, it is easy to quantize. And after that, you take quantum Hamiltonian reduction, which is also something well defined. So you get some natural quantization of this Poisson structure on Lamont and Drinfeld zastava space by some natural procedure.
Very good.
Okay, so maybe that's all. So I have to finish.
Two very difficult questions. Do you know the analog for the partial flag varieties for Gerasimov?
For partial flag variety, actually, almost nothing changes. You just have to consider not one-dimensional WI, but WIs of some dimensions, some collection of dimensions.
Second very difficult question is about integrable systems on this space. Are there some natural integrable system which live on this space?
Integrable system. There is some natural integrable system given by the coordinates xi. So because xi they commute.
So I have some idea about the full Toda chain, full Toda system, if you know. It's related with this construction.
Right. Toda system. Yeah, it is.
It is exactly to the Barrel subalgebra. That's why I'm asking you. But I'm sure that it is the same Poisson structure. In this case, it is just a Poisson structure in the Barrel subalgebra. But the integrals are more complicated, more elaborated.
Okay.
But
so
my question for some future discussion. I'm very sorry.
Yeah. So we can discuss it later, maybe.
Railways are strict organized. Leonid, thank you very much.
Thank you for inviting me.
Maybe
thank you very much.
More questions? No. Okay, thank you once again.
Okay.
Bye.
Bye. See you later.